Hello again. I'll try this again. The mic got turned off halfway through the other one, so we'll start over. So in this, inorganic, we talk a lot about throughout the semester. It will depend on how you draw things and what detail you put into it. The more detail you put into it, the better off you will be. Okay, but in this, for this reaction, we have, red pen, the lone pair on the nitrogen. We have the arrow going to the carbon atom here. Okay, we have the double-headed arrow with two arrowheads on it. That signifies two electrons are moving. If we have drawn an arrowhead differently, it would signify one electron moving. And this one goes from the carbon-chlorine bond to the chlorine itself. So that gives us the chlorine with 4 lone pairs around it, and 4 lone pairs gives the chlorine a negative charge, the nitrogen with a positive charge. So we just have to be careful how we show things in this and how we draw it, and make sure as you're going along, watch the videos I make, watch the stuff in the YouTube, ask questions, whatever you need to do to be successful in this, but be very careful how you draw things as we're going along. It's very important to be careful about that. So we have the periodic table. We know we have the nonmetals over here on the left, all of these. And then we have the metals over here on the right, and then the stair step that goes down roughly through here, separating them out. Okay, and in this, the only ones that we really worry about a lot are the ones in this row from lithium over to neon. They have to follow the octet rule because we only have 4 orbitals around them, 1s and 3p orbitals. So each orbital, no matter what kind of orbital it is, it can only hold 2 electrons. So we have 4 orbitals. We can hold 8 electrons in any one of those atoms as a maximum. We can't go over that, so don't draw anything with a carbon with 10 or 12 or 16 electrons around it. It hurts. Carbon only has 4 orbitals, so it can only have 8 electrons total. Okay, so be careful about that as you're going along. And as we'll say later, when you get down below, in the 3rd row or 4th row across, you can have more electrons around those because they have more than just the s and p orbitals around them. Okay, so if we want to draw the Lewis structures for things, we start with the atom. We start with, say, the oxygen atom here. Oxygen has 6 valence electrons, so we start with putting 1 on each of the oxygen, around the oxygen single, and then that's 4 because we have 4 orbitals, and then we still have 2 more electrons, so 2 of them have to be paired up. So oxygen is going to look like this with 2 pairs and 2 single ones. Okay, carbon, we only have 4 valence electrons. It's only going to have 4 electrons around it. It's going to have to form 4 bonds, period. Okay, no exceptions about that. Nitrogen, we start with our 4, but we have 5 on nitrogen, so one of them is going to have to pair up, so it's going to have 3 bonds, 1 lone pair. Okay, oxygen is going to have 2 bonds and 2 lone pair because we have 2 pairs already made on it. Hydrogen only has 1 orbital, 1 electron on it, so it's only got 1 orbital, so it can only form 1 bond. Chlorine, we start with our 4, and then we know chlorine has 7, so 3 of these are going to have to be paired up, so chlorine's going to have 1 bond and 3 lone pair. And then neon, you start with 4, and then you add 4 more because it has 8, and that shows neon's full to the octet. Neon's useless. We won't ever talk about it again. Okay, so there are choices Carbon 4 bonds, nitrogen 3 bonds in a lone pair, oxygen 2 bonds and 2 lone pairs, and the chlorine 1 bond and 3 lone pairs because of the number of electrons around it, to what it needs to get to 8. Okay. Drawing the Lewis structures of a small molecule, second row elements, carbon, nitrogen, oxygen, and fluorine can only have 8 electrons around them because they have the only have the s and the p orbitals around them. They can't deviate from that. Don't try anything fancy. Don't go over 8. Boron and beryllium have fewer than 8 electrons around them because they're deficient, because beryllium only has 2 electrons in its valence shell, so it can only form 2 bonds, so it's only going to have 4 around it. Boron has 3 electrons around it, so it can only form 3 bonds, so it only has 6 electrons around it. So they're more reactive because they're electron deficient. We'll get into that later when we talk about get into reactions and use boron for a couple reagents in the third test. So second row elements only have s and p orbitals. They only have 3 p orbitals, 1 s orbital, 2 electrons per orbital. 2 times 4 is 8. Okay. Third row elements end up with an s, a p, and d orbital available to it, so they can go over 8 because they have the d. They can go up to 18. Sulfur and phosphorus are the only 2 we'll really talk about going over 8. They can have 10 or 12 around them depending on what you have. So, but those are special. Okay. When drawing the Lewis structure for a molecule, satisfy the octet rule and then place extra electrons in any atom that can have more than 8. Okay, don't start throwing any extra in anywhere. So if you have HF and we were to draw the Lewis structure for it, first we start with the bond between the hydrogen and the fluorine. That's 2, and then we throw in the 3 lone pairs, so HF would look like that. Oxygen, we know, has 2 lone pairs and 2 bonds, so water is going to look like that. Ammonia, 3 hydrogens on the nitrogen with a lone pair. Methane is going to be 4. And fluorine only wants 1 bond, so it's going to have a bond between the 2 fluorines with 3 lone pairs on each. And then the acetylene, when we start with, we only have 2 bonds on each chlorine or each carbon, so the only way we can get it up to 8 4 bonds is to have a triple bond between the 2 carbons. Exceptions, BF3, as we said, boron has 3 electrons on it, so when we add the fluorine, BF3 is going to have 3 bonds to 3 fluorine, so the boron will only have 6 electrons around it, and the molecule would just be this with the 3 lone pairs around each fluorine. The boron only has 6 electrons. It's more reactive. That's all about it. Okay. The SF6, the sulfur hexafluoride. Sulfur has 6 electrons. Each one is used in making a bond to a fluorine. We throw in a bunch of lone pairs, 3 on each fluorine. The sulfur gets no lone pairs because it has used all its electrons in forming a bond to each of the fluorines. So SF6, the sulfur has 12 electrons around it because it has the d orbital. Okay. To calculate formal charges, remember, you've done this back in general chemistry, I'm sure, but you take to figure out the formal charge, you take the valence electrons for the free atom, so all 3 of these are carbon, so that's a 4, okay, and then from that free electrons on that atom and valence electrons, we will subtract the number of valence electrons assigned to each of them in the molecule. So in this first one, we have 3 bonds to it, no lone pairs, so 3 bonds. Half of the electrons in the bond are assigned to the carbon. The center one, half of them are assigned to the other one. So that's 3. There are no lone pairs, so 4 minus 3 gives us a +1. In the center one, we have 4 minus 4 for bonds, no lone pairs again, so 4 minus 4 is 0. So our center carbon in the middle one is formal charge of 0. And the last one here, we have a carbon with 3 bonds. Whoops, drew it to the wrong number. And then in a separate color, let's put the lone pair electrons, which these two are both 0. And so in the last one here, we have 4 for the valence electrons on carbon in the periodic table, and subtract from that the number of electrons in bonds that are assigned to the center one, the number of bonds, 3, plus the number of lone pair electrons. It has 1 lone pair, 2 electrons, so 3 plus 2, so 4 minus 5 gives us a -1 for that one. Now, when we have a formal charge on a nitrogen or oxygen, we have to show the lone pairs on it or the charge to know what it really is. Because if we draw something like this, we can't say anything about the formal charge of it because we don't know how many electrons are really around that nitrogen. Okay, it could be a plus, it could be a minus. You know, we don't have the information we need. If we have 1 lone pair on it, we have 5 electrons for nitrogen. And so in this, when we think about the first one, it has 5 electrons assigned to nitrogen from the periodic table, and we subtract the number of electrons assigned to it in this ion. It has 2 bonds, and it has 2 electrons in the lone pair, so 5 minus 4 gives us a +1. So the first compound is a +1. The second one, we have 5 assigned to it from the periodic table, and we subtract from that 2 electrons assigned to it in these 2 bonds, plus 4 electrons from the lone pairs on it, because all of those electrons are only on that nitrogen. So 5 minus 6 gives us a -1. So we have to be careful how we draw things so we get all of the information we need in the problem to make sure we can answer it right. Okay, so the next one down here, if we were to draw the sulfate ion here, SO4 2-, the first answer we would give is with the sulfur with 4 single bonds to the oxygens. But if we drew it this way, we know each of these oxygens has to be a -1. So if overall the SO4 2- ion is a -2 and we have 4 -1s, the sulfur has to be a +2. Okay, now can you have a sulfur with a +2? Well, you can, but it's not very likely because that's a lot of charge on that one little atom. So it would be better to draw it where instead of having all of those charges on every atom in the molecule, we draw some of them so that they have a formal charge of 0. So if we put 2 of the lone pairs from the side oxygens and make them double bonds, this oxygen here, the first one I drew in, that one has a formal charge of 0 because it has 2 bonds and 2 lone pairs. This one on the left side, also 0, 2 bonds, 2 lone pairs. This oxygen on the top is a -1, and this oxygen on the bottom is a -1. So now we have 2 minuses, 2 neutral, so the sulfur also has to be neutral to make it add up to 0. And sulfur, if we calculate it out, it has 6 electrons assigned to it in the periodic table, and we subtract from that the electrons in bonds, 6, because we have 6 bonds, plus lone pair, 0, so 6 minus 6 gives us 0. So the formal charge on that sulfur is 0, which is the way we want it. So we only have 2 atoms instead of all 5 with a charge on it. Okay, types of bonds we have the ionic bond, which is between a metal and a non-metal. And an example of this would be sodium chloride, where the sodium's a metal, the chloride's a non-metal, and we get a salt out of it. A covalent bond is between two nonmetals, and this is two nonmetals that have equal or near equal electronegativity. The polar covalent is between two nonmetals with different electronegativity. Okay, and we know electronegativity is the ability of the atom to pull electrons towards it in a bond. Okay, so between HCl, the hydrogen's less electronegative, so it'd have a partial positive. The chlorine would have a partial negative with a dipole moment towards the chlorine in that. It's a polar molecule. But just because you have a polar bond doesn't mean you have to have a polar molecule. So hydrogen fluoride the hydrogen has a partial positive, the fluorine is partial negative. It has a pull towards the fluorine, so we have a dipole moment towards the fluorine. Chloroform and carbon tet, while they both have bonds between carbon and chlorine, the chloroform is a polar molecule because while each of the bonds to carbon are pulling, or bonds to chlorine from the carbon are pulling towards the chlorine, the bond to the hydrogen, which was poorly drawn, is not as polar because the hydrogen's not near as electronegative as chlorine. So overall, these are all pulling towards the chlorines, but overall we have it pulling from, here, let's do that this way, pulling across the molecule that way, where the side with the hydrogen is a partial positive and the chlorines are all pulling electron density towards them. They're roughly on one side. And the next one, each of these are pulling equally powerful towards each other. So this one is nonpolar because they have the equal pull towards each of the chlorines. Okay. In resonance structures, in this first one, in the allocation, we have a positive charge. There are no electrons in that positive charge, so all we can do is send the electrons from the double bond to go towards the positive charge. So those are our two resonance structures we can draw for the allocation. The nitrate, and in this, when we draw resonance structures, we always start with the spot where we have the most electron density. In the first one, it was the double bond because the positive charge doesn't have any electron density because it's a positive charge. In the second one, the nitrate, one of the oxygens out here on the edge where they're negative charge, that's your most electron density. You're going to take electrons from it, form a double bond, and then break a double bond, and draw your resonance arrow. And then that oxygen to the left didn't change. The oxygen on top gained a lone pair, and the oxygen on the right formed a double bond to it. So the nitrogen's still positive, and each of those oxygens are negative. And then we can draw our last one where we take the electrons from the negative on the left and send it to the carbon or the nitrogen oxygen double bond on the right. And we get our third resonance structure where nothing changed to the top oxygen. We got a double bond over here on the right, a single bond here, negative charge, positive charge. So as this shows, we can start our resonance structures from either of the oxygens because the one below that I drew in on the computer when I made this started with the oxygen on the left. It doesn't matter which of those two oxygens you start with because they're both negative charged. Okay, they both have equal amount of electron density on them, so whichever way you want to draw them is fine. Now we have the problem that I told you to work on in class at the end. The bottom one here is the one we did in class where we drew the resonance structures for you before you left. Chasing the positive charge. Now I'm going to draw this with the line angle formula, and then before I close this I will draw the starting material again, but we're just chasing the positive charge just like we drew it in class throughout, and then send it back down to get to our resonance structure we started with, where the double bonds are alternating from what we started with. And the one on the top, we have a nitrogen with two bonds, two lone pairs, so it's got a negative charge. So all we can do is send the electrons down to form a double bond and break a double bond. And we then have a negative there, and the NH. The NH is neutral because it has three bonds around the nitrogen. And we just chase the negative and chase it around, or take it around the ring, forming a bond and breaking a bond as we go along. And there was that, and then do it again. And now look where we are. We're here with the negative here and the NH and double bond, and we can send it back to the nitrogen. And we have the resonance structure of what we started with. And these are just showing what can happen with this molecule to help us with how they react later on as we do all of this. Okay, and the bottom one, the ester here, our functional group, is an ambident nucleophile. It can be protonated on either of the two oxygens because they both have two lone pairs, and we have to decide which one is where we will protonate it. Which of these two protonated esters will we protonate it at? Which one's more stable? So how do we figure that out? We need to think about electronegativity or resonance. Those are the only two things we've talked about so far. Electronegativity, oxygen, hydrogen, in both of them for the bond, that's the same, so we can't use that. So it's going to have to be resonance structures. So how can we draw a resonance structure of the top one? We send the electrons towards the oxygen of the double bond, and our resonance structure is going to look like that, with a positive now on the oxygen of the OCH3. On the second one, all we can do is send electrons towards the carbonyl again. So when we draw it, we get an oxygen with a negative charge. We have the CH3, better draw the CH3 up here too. Oxygen with a double bond, hydrogen and a methyl. So now this oxygen is a +2, and between these two resonance structures, the oxygen with the +2 is not going to happen because it's such a small atom. We can't get a +2 on it. So this will not happen because of the +2 charge required on that oxygen. So the only one we can form is this one because it gives us the same separation of charge between the two resonance structures. So that is a very good resonance structure to have. So this would be the one where we would protonate that carbonyl, the carbon-oxygen double bond in that. Okay, so here's chapter 1. Okay, I'm going to quit talking for the day. If you have questions about anything we talked about today in this, I'm going to post this in D2L and all. If you have questions, feel free to email me tomorrow or whenever. Come by my office. I'll be in tomorrow late morning and probably be there till 5 or 5:30. Okay, so check it out. ask questions, send me an email, whatever you need to do to make sure you're successful in here. Okay, have a good day. See you all later. Okay, sorry. I'm going to do another page or two. I thought I was done with the chapter. So here we have the structural formula. If we draw it out with everything, showing all the carbons and hydrogens, it takes a long time to draw it, so we'll write it shorter. The molecular formula, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. 1 nitrogen and 2 oxygens. Okay, if we were to draw the condensed structural formula, we would draw it where we have the CO2H, CH2, CH2, CH, double bond, CH, C, C, CH2, NH2. It still takes too long to draw it like that, so we're much better off if we draw it where each carbon along the line is just a point. So we have 2 CH2s, and then we have the carbon of the double bond, and then that goes to the carbon of the triple bond, and then the CH2 and the NH2. So we can draw it much quicker with the line angle formula. So practice that. Look, as you see things in the showing the Lewis structure, you know, cut it down and draw the line angle formula to give you practice at it, a bond line formula, so you can draw it faster as you're going along. Okay, hybridization. Here's the best part of chapter 1. Hybridization talks about what is the molecule, how is it put together, how is it held together, what kind of orbitals is it using. If we talk about methane, okay, we know that methane, here, we'll draw it down here. Methane, we know the hydrogens on that carbon all react the same. So methane, CH4, has to have 4 equivalent orbitals. Well, carbon has 1 s orbital and 3 p orbitals on it, so that doesn't help us explain that. So we need to think about what can happen. And what happens is, in hybridization, we take all the s and the 3p orbitals, mix them all together, and then pour them out equivalently, and we get 4 sp3 orbitals. So anytime, what you need to do is to think single bonds, double bonds, triple bonds, and lone pairs. Each of those counts as 1 when you're thinking about this. Okay, so in methane we have 4 single bonds, we need 4 equivalent orbitals. We're going to have an sp3, so methane, the carbon, is sp3 hybridized. If we go to ethylene, if we draw ethylene, we have this, and as we said with earlier, single bonds, double bonds, triple bonds, and lone pairs all count as 1. In ethylene, we have a hydrogen, and a carbon off of it, so we have 1 single bond, 1 single bond, 1 double bond. Those all count as 1, so we need to mix an S and 2 P's together. So each of the carbons in ethylene is sp2 hybridized. Okay, if we think about carbon dioxide, okay, we have 2 pi bonds on each of the carbons, so we only have 2 bonds, so it's going to be an S and a P, so it's going to be sp hybridized with 2 p orbitals. Now this is the carbon, not the oxygens, with 2 p orbitals on it, and the p orbitals are what make up the pi bonds on the carbon. Okay, so that carbon is sp hybridized in carbon dioxide. Okay, And the carbon of ethylene, either of the carbons of ethylene, is sp2 hybridized. So that's the hybridization for both of those. Remember what we said about it. It had that p orbital left over from the hybridization. So each of the carbons has a p orbital on it, and that's what's used to make the pi bond. In the last page where we had, it was sp hybridized, so we have these two p orbitals that we didn't use so far in the hybridization. They're left over to make the bond strengths and bond lengths. The shortest bond length is ethylene. The strongest bond length is ethylene because we have the 3 bonds between the two. Okay, so in ethylene, or ethine, I mean, what did I say a second ago? Ethine has the shortest bond and the strongest bond because you have the triple bond between the two. Ethene, C2H5, each of the carbons is sp2 hybridized. So each of the hydrogens is in an s orbital. Then the carbons, that's all going to be in the plane of the board, and each of the carbons is going to have a p orbital that goes behind the plane and comes out of the plane. And then the overlap between that is what makes up the pi bond. So it has one p orbital, and okay, so that pi bond is the overlap between those two p orbitals in that. Now if we go to ethine, we have a carbon that's sp hybridized, as we said, to each of the hydrogens. So we have that, and then each of those carbons still has 2 p orbitals on it, as we said on the pi bond. So one of them will be in the plane of the board, plane of the iPad, with the overlap between the two. The other one will be 90 degrees to it, coming towards and going behind each of those. We'll draw it blue to differentiate, and the overlap in that one makes the second pi bond. So the ethine has, acetylene has 2 pi bonds on it with 90 degrees apart from them, and each of the pi bonds has a p orbital on the carbon. So there are 2 p orbitals on each carbon, 90 degrees to one another, that make up the 2 pi bonds. Atomic shapes. So we've drawn the Lewis structure so far. So if we draw again water, ammonia, and methane, first off, you know what the hybridization of each of these is from what we've said. They all have 4 things around them, so they are all sp3 hybridized. So then what can we say about carbon? 4 bonds. What shape is it? We know it's tetrahedral, where we have the tetrahedral shape with 2 of them in the plane, 2 out of the plane. The bond angle, as we said in class, is 109.5 for it. When we go to the ammonia, it's still sp3 hybridized, but it is so sorry about that. My finger hit something. So the nitrogen is going to look just like a carbon, but it's going to have 1 of them with a lone pair, and then the other 2. And maybe I'll draw the, if I can erase it, probably can't erase it. No, can't erase it. So the carbon, we could have drawn, well here, let's go to add a new page in. Perfect. That's what's wrong. Sorry. So for the oxygen, it's going to have 2 and 2 lone pairs. The nitrogen is trigonal pyramidal. With a bond angle slightly less than the tetrahedral, and then the water is bent with a bond angle even less still of about 104.5. Okay, so there's the hybridization, the shape of the molecule, tetrahedral, trigonal pyramidal, and the bond angle. Okay, and as we're going along, we need to be careful about all of that, that we do that as we're using them. Okay, so there's that. Now I need to stop the video and get to the end of this so I can find the next page. Hold on for a minute. Be right back. Okay, the last page of this chapter 1 is filling in the Lewis structure for a molecule where we don't have everything. So the first thing we want to do is put in the lone pairs on all of the atoms. Oxygen wants 2, nitrogen wants 1, carbon wants 0. So we'd have those lone pairs, and then we mix in the double bonds. So this oxygen, the top oxygen, oxygen number 1, has 2 bonds, 2 lone pairs. It's good. Oxygen number 2, this one here, has 1 bond and 2 lone pairs, so it needs a double bond. And then carbon 9 is good because it has 4 bonds. Carbon 8 is good, it has 4 bonds. Nitrogen has 3 bonds and a lone pair, it's good. Carbon 7, this one here, has 4 bonds, it's good. Carbon 10 is missing 2 bonds, it needs to have a triple bond. It can't go to 7, it has to go to 11. Because 7 already has 4 bonds to it. And then that gives 10 and 11 carbons, 4 bonds on each of them, so they're good. And then we need to put in 2 double bonds inside the ring because those 4 carbons need 1 more bond each, so we have to have a double bond in there. Okay, so there's the Lewis structure. We draw in the lone pairs first so we know where they all are, and then fill in double bonds on the atoms that do not have 8 electrons around them. Okay, and remember, oxygen always wants 2 bonds, 2 lone pairs, nitrogen 3 bonds, 1 lone pair, and then go from there. So now we're supposed to ask or answer, what's the hybridization for that? So oxygen 1, it's got 4 things, so it's sp3. Oxygen 2 is sp2. Nitrogen 1 is sp3. Carbon 1, 2, 3, and 4 is sp2. Carbon 5 and 6 are sp3 because they have 4 things around it. Carbon 7 is sp3. Carbon 8, this one here, is sp3. 9 is sp2. And 10, 11 are sp because they each have 2 things around. Okay. And then the last thing about this is isomerism. Constitutional isomers or structural isomers differ only in their bonding sequence, so they're not connected in the exact same way. So in the first one we have 6 carbons in a straight chain, in the second one we have 5 carbons with a methyl off of it. Those are constitutional isomers, structural isomers of each other. Stereoisomers differ in not how they're, what the in their bonding sequence. They're bonded in the same sequence. There's just difference in them. In this, we have the trans versus the cis alkene in that, and we'll get into that a lot later on, so don't worry about that as we're going on. So this all is what you need for chapter 1. We'll finish this part at the start of class next time and then go on from there into chapter 2. Okay,